There's a paradox hidden in the sky. The higher you climb, the thinner the air becomes, and yet it is in this near emptiness, in the cold silence of the upper atmosphere, that the fastest and most graceful flight occurs. Down here, where the air is thick and warm, birds labor heavily against the wind. But 11 kilometers above your head, where the temperature drops to -50 degrees and the air holds barely a quarter of its sea level density, aircraft glide through a realm of strange and beautiful physics. The rules change at altitude, the silence deepens, and flight becomes something closer to floating through space itself. Tonight, let these soothing facts about the quiet physics of high-altitude flight carry you gently toward deep sleep. Tonight, we explore the science of aerodynamics in the sleep documentary for curious minds seeking rest. From the invisible forces that shape every wing and every feather, to the thin boundary layers where turbulence is born, to the silent corridors of the stratosphere where commercial aircraft cruise at the edge of the atmosphere. This is the story of how objects move through air and how air moves around objects. These are the principles that allow a bird to hover, a glider to soar without an engine, and a jet to cross oceans while its passengers sleep peacefully above the clouds. This is sleepy science, where the physics of flight becomes a lullaby and knowledge becomes rest. Welcome to Drowsy Discovery, your sleepy science channel for peaceful nights. Over the next 2 hours, over 100 gentle facts about aerodynamics and high-altitude flight will guide you through the invisible forces that govern the sky. There is nothing to memorize, nothing to remember. Just listen and let your mind drift into deep sleep. Have you ever wondered why aircraft fly so high, or how a wing creates lift from nothing but moving air? You are not alone. If this documentary for sleep brings you peace, consider subscribing to join our community of curious minds, and perhaps share these facts to fall asleep to with someone who needs a calm night. Now take a slow breath and let your shoulders ease. Feel the weight of your body sinking softly into stillness, as though you were rising gently through layers of atmosphere, leaving the noise of the earth far below. The sky has waited for billions of years. It will wait patiently for you to fall asleep in its endless quiet. Let us begin. The air at cruising altitude is so thin that a human would lose consciousness within seconds without pressurization. At 11,000 meters above the Earth, where commercial aircraft glide through their journeys, the atmosphere has thinned to a quarter of its sea level density, and the oxygen that keeps your brain alive has become so scarce that without pressurization, you would lose consciousness within 15 to 20 seconds. This altitude is known as the death zone not because of cold, but because the partial pressure of oxygen falls below what human blood can absorb. The aircraft cabin is pressurized to simulate an altitude of around 2,000 meters, a compromise that keeps you alive while reducing structural stress on the fuselage. And throughout your flight, unseen systems work continuously to compress thin outside air and deliver it to your lungs. It is a quiet miracle that you breathe and sleep while crossing oceans at the edge of survivability. Lift is not created by air hitting the bottom of a wing, but by the shape of the wing bending airflow around it. For centuries, people imagined that wings worked like hands pushing against water, but the truth is far more elegant. A wing generates lift not by batting at the air, but by persuading it to curve, to accelerate, to change direction in ways that create differences in pressure between the upper and lower surfaces. The curved upper surface forces air to travel faster, creating lower pressure above, while the flatter lower surface maintains higher pressure beneath, and this difference pulls the wing upward from above. If you could see the invisible streamlines flowing around a wing, you would witness air bending in graceful arcs, hugging the surface as though drawn by some magnetism, and separating at the trailing edge to continue its journey. The wing is not fighting the air but dancing with it. Flight is not conquest, but collaboration. The Bernoulli principle explains why faster-moving air creates lower pressure. Daniel Bernoulli, an 18th-century Swiss mathematician, discovered a relationship so fundamental that it governs everything from the curve of a cricket ball to lift beneath a wing. His principle states that within a flowing fluid, velocity increases as pressure decreases, as though movement and pressure are two forms of energy trading places. When air speeds up over the curved top of a wing, pressure drops, and this low-pressure region above creates the suction that we call lift. You can feel this by blowing across the top of a sheet of paper and watching it rise toward your breath, the faster air above creating lower pressure than still air below. Bernoulli never imagined the jets that would one day cruise through the stratosphere, but his quiet observation made flight possible. Some discoveries need centuries to reveal their full significance. A wing does not push air down so much as it persuades air to curve around its surface. The secret of flight lies not in force but in redirection, in the way a shaped surface convinces air to follow a curved path and creates the pressure differences that lift aircraft into the sky. Air approaching a wing does not collide and bounce, but flows smoothly around the leading edge, accelerating over the upper surface and departing at the trailing edge with a slight downward deflection. This turning of the airflow, known as circulation, generates lift not through brute strength, but through elegant geometry. The shape of the wing is called an aerofoil, and its curves have been refined over more than a century, tested in wind tunnels, simulated in computers, and proven in billions of kilometers of travel through the atmosphere. A wing is an invitation, and the air accepts it willingly. The sky yields to those who understand how to ask. The boundary layer is a paper-thin region of air that clings to every surface moving through the atmosphere. When an aircraft moves through the sky at hundreds of kilometers per hour, a thin layer of air directly against its surface barely moves, held by viscosity, the stickiness all fluids possess. This layer, sometimes only a fraction of a millimeter thick, is called the boundary layer, and within it air velocity changes from zero at the surface to full speed a short distance away. The behavior of this invisible skin determines much of the drag an aircraft experiences, because energy is lost in shearing motion between layers sliding past one another. If you could touch the wing of a cruising aircraft, you would feel not rushing wind but trapped air, molecules trembling between stillness and motion. The boundary layer is where physics negotiates the relationship between solid and gas. Even in the fastest flight, something remains still. Turbulent airflow wastes energy, while laminar flow moves in smooth, parallel layers like silk sliding over glass. There are two ways air can move across a surface, and the difference determines how much fuel an aircraft burns and how quietly it slips through the sky. Laminar flow is the graceful state where air molecules travel in orderly parallel paths, each layer sliding over the one beneath like silk over a polished table. Friction is low, energy loss minimal, and the boundary layer thin. But laminar flow is fragile, and small disturbances, a rivet head or speck of dust, can trigger turbulence where orderly layers collapse into chaotic swirls, wasting energy through friction. Turbulent flow creates more drag yet clings to surfaces stubbornly, preventing the separation that leads to stalls. Designers spend years maintaining laminar flow because every smooth square meter saves fuel. Order and chaos coexist across the skin of every aircraft. And from the delicate layers of air clinging to wings, we now turn to the invisible architecture of the atmosphere itself. The atmosphere is divided into distinct layers, each with its own temperature, pressure, and behavior. The ocean of air surrounding our planet is stratified into distinct layers, each with its own character and physics. The troposphere, where we live and weather happens, extends from the ground to roughly 11 kilometers at the equator, and temperature drops steadily with altitude. Above lies the stratosphere, a calmer realm where temperature increases due to ozone-absorbing ultraviolet light, creating a stable inversion that suppresses vertical mixing. Higher still are the mesosphere, thermosphere, and exosphere, each progressively thinner with peculiarities affecting spacecraft differently. Commercial aircraft cruise in the lower stratosphere because its stability offers refuge from storms below. The layers are invisible walls, boundaries marked not by solid barriers but temperature gradients. We live at the bottom of an invisible ocean with many floors. Commercial aircraft cruise in the lower stratosphere, where the air is calm and weather rarely reaches. When you settle into your seat and the captain announces cruising at 35,000 feet, they are telling you the aircraft will climb above most weather into a region designed for smooth flight. The lower stratosphere begins above the tropopause, and air here is remarkably stable because temperature increases with altitude, suppressing the currents that create clouds and turbulence below. Commercial aircraft cruise here because thin air creates less drag, allowing higher speeds with less fuel, and smooth conditions provide comfort for passengers who sleep as they cross oceans. The stratosphere is peaceful, a realm of endless blue sky above and white cloud decks far below, where flight reaches its most elegant expression. This is where journeys happen without interruption. This is the quiet corridor of the sky. The tropopause is the boundary between the turbulent troposphere and the stable stratosphere above. Rising through the atmosphere, there comes a point where temperature decline suddenly stops, where air transitions from the chaotic troposphere to the calm stratosphere above. This invisible boundary is the tropopause, marking one of the most significant transitions in our atmosphere, a ceiling above which thunderstorms cannot grow and below which most weather remains trapped. The altitude varies with latitude, reaching nearly 18 kilometers above the equator where warm air rises highest, and dropping to around 8 kilometers over the poles. Jet aircraft crossing latitudes must adjust their cruising levels to stay above the tropopause. The tropopause is not a rigid surface but a gradient, a zone where physics shifts from one regime to another. It is a boundary you cannot see, yet it separates two different worlds of air. At high altitude, aircraft engines must work harder because there is less oxygen to burn fuel efficiently. Every jet engine is a controlled fire requiring oxygen, and at cruising altitude where air density drops to a quarter of sea level values, engines must compensate for scarcity. The solution lies in compression, in spinning fans and blades that draw enormous volumes of thin air and squeeze it to densities higher than sea level before mixing with fuel and igniting. A modern turbofan can compress air 40 times or more, transforming sparse stratosphere into a dense mixture capable of sustaining powerful thrust. This is why jet engines are most efficient at high altitude, because although they work harder to compress thin air, reduced drag and lower temperatures compensate, allowing aircraft to cruise faster while burning less fuel per kilometer. The physics of high-altitude flight is a balance between scarcity and efficiency. In thin air, engines do more with less. Jet engines compress thin air hundreds of times before mixing it with fuel and igniting it. At the heart of every jet engine is a sequence of spinning blades designed to take the thin, oxygen-poor air of the stratosphere and squeeze it into something useful. The compressor section, a series of rotating fans and stationary vanes, draws in enormous volumes of air and passes it through progressively smaller chambers, raising its pressure and temperature with each stage. By the time the air reaches the combustion chamber, it has been compressed 40 times or more, its density now greater than the air at sea level. Fuel is then injected and ignited in a continuous, controlled explosion that powers the turbines driving the compressor, while the remaining exhaust is expelled at tremendous velocity, generating thrust. The entire process happens thousands of times per second, a symphony of heat and pressure conducted within a metal tube. In thin air, the engine creates its own dense atmosphere. The condensation trails behind aircraft are artificial clouds formed when hot exhaust meets freezing air. When jet exhaust leaves an engine at temperatures exceeding 500 degrees, it carries with it water vapor from the combustion of fuel, and when this hot, moist air meets the freezing atmosphere at cruising altitude, the water vapor condenses instantly into tiny ice crystals. These crystals form the white lines that trail behind aircraft, known as contrails, artificial clouds that can stretch across the entire sky. Whether a contrail forms depends on the temperature and humidity of the surrounding air, which is why some aircraft leave long, persistent trails while others leave none at all. In very cold, humid conditions, contrails can spread and linger for hours, eventually joining with natural cirrus clouds and affecting local weather patterns. Every long-haul flight writes a temporary signature across the sky. It is a reminder that even the air remembers our passage. And from the clouds that aircraft leave behind, we descend to the forces that govern every moment of flight. 4 fundamental forces act on every flying object: lift, weight, thrust, and drag. Every aircraft, every bird, every falling leaf exists within a constant negotiation between 4 fundamental forces. Lift pulls upward, created by the wings shaping the airflow around them. Weight pulls downward, the Earth's gravity insisting that everything must eventually return. Thrust pushes forward, whether from engines, muscles, or the wind itself. Drag pushes backward, the air resisting every attempt to move through it. When lift equals weight and thrust equals drag, an aircraft flies straight and level, suspended in a state of perfect balance. Tilt any of these forces and the aircraft climbs, descends, accelerates, or slows. Pilots spend their careers learning to feel these invisible hands, adjusting constantly to maintain equilibrium. Flight is not the absence of gravity, but a delicate dance with all 4 forces. Balance is everything. Drag is the invisible hand that resists all motion through air, growing stronger as speed increases. Every object moving through air must push molecules aside, and those molecules push back with a force we call drag. At low speeds, drag is gentle, almost imperceptible, but as velocity increases, it grows not in proportion but exponentially, so that doubling your speed quadruples the drag you must overcome. This is why it takes so much more fuel to fly fast than to fly slowly, why supersonic aircraft consume fuel at rates unimaginable for subsonic flight. Drag comes in many forms: the friction of air sliding over surfaces, the pressure building at the front of the aircraft, the turbulence swirling behind. Engineers shape every surface, every rivet, every antenna to minimize this invisible resistance. The sky is generous, but it asks a price for passage. Drag is the tax levied on all who would move through the atmosphere. Induced drag is the price paid for generating lift, a consequence of the wingtip vortices that spiral behind every wing. When a wing generates lift, it creates a pressure difference between its upper and lower surfaces, and at the wingtips, this pressure difference causes air to spill over from below to above, forming spinning vortices that trail behind the aircraft like invisible tornadoes. These vortices consume energy that could otherwise be used for forward motion, creating a form of drag that increases as the wing works harder to generate more lift. Induced drag is unavoidable, a tax imposed by physics on every flying object that dares to leave the ground. It is strongest at low speeds and high angles of attack, diminishing as the aircraft accelerates. The larger the wingspan, the weaker the vortices and the lower the induced drag, which is why gliders and albatrosses have such long, narrow wings. Lift always comes with an invisible cost. And as you rest with these thoughts of invisible forces, there is no need to hold onto any of them. Let them pass through you like air flowing gently around a wing, like sleep science drifting softly through the night. Take a breath if you wish, and let your body settle a little deeper into stillness. Winglets were invented to reduce the energy wasted in wingtip vortices. If you look at the wings of most modern aircraft, you will notice small vertical extensions at the tips, curved gracefully upward like the tips of an eagle's feathers in flight. These winglets are designed to interfere with the formation of the wingtip vortices that waste so much energy in induced drag. By blocking the spillage of high-pressure air from below the wing to above, winglets reduce the strength of the vortices and recover some of the energy that would otherwise be lost in swirling air. The fuel savings are modest, just a few percent, but over the lifetime of an aircraft flying thousands of hours, those small percentages add up to vast quantities of fuel and substantial reductions in emissions. Winglets are one of those elegant solutions that seem obvious in hindsight. Sometimes the smallest changes at the edges yield the greatest returns. The angle of attack is the angle between a wing and the oncoming airflow, and it determines how much lift is generated. A wing does not simply cut through the air but meets it at an angle, and this angle determines everything about the lift it produces. Increase the angle of attack and the wing deflects more air downward, generating more lift but also more drag. Decrease it and lift falls, allowing the aircraft to descend or accelerate smoothly. Pilots control this angle constantly, raising the nose for takeoff and landing, lowering it for cruise, adjusting carefully for every gust of wind and every change in speed. The instruments in the cockpit show airspeed and altitude, but experienced pilots feel the angle of attack in the subtle vibrations of the controls, in the sound of the air rushing past the fuselage. It is the most fundamental relationship in flight. The angle between wing and wind defines what the sky will allow. If the angle of attack becomes too steep, the airflow separates from the wing and lift collapses in a stall. There is a limit to how steeply a wing can meet the oncoming airflow. Beyond a certain critical angle, the smooth laminar flow over the upper surface can no longer cling to the wing and separates into chaotic turbulence, causing lift to collapse suddenly and dramatically. This is called a stall, and it has nothing to do with the engines, only with the angle of attack exceeding what the wing can safely sustain. A stalled wing does not stop flying entirely, but loses most of its lift, causing the aircraft to pitch nose down unless the pilot reduces the angle of attack to allow the airflow to reattach smoothly. Pilots practice stall recovery repeatedly, because recognizing the early signs of a stall and responding correctly can mean the difference between a safe recovery and disaster. The sky forgives much, but not this. Stall speed changes with altitude, weight, and the configuration of the aircraft. The speed at which a wing stalls is not fixed but shifts according to conditions. At higher altitudes where the air is thin, the wing must move faster to generate the same lift, so stall speed increases. Heavier aircraft also stall at higher speeds because the wing must work harder to support the additional weight. Deploying flaps and slats changes the wing's shape, lowering the stall speed and allowing slower, safer approaches for landing. Pilots must calculate stall speeds before every flight, accounting for fuel load, passenger weight, temperature, and altitude. The margins between safe flight and stall can become surprisingly narrow at high altitude, where thin air and high speeds conspire to squeeze the window of safety. Understanding stall speed is not academic knowledge, but a matter of life and death. The numbers in the cockpit are more than data. The coffin corner is a narrow band of altitude where the margin between stalling and overspeeding becomes dangerously thin. At very high altitudes, where the air is thin and cold, an aircraft faces a strange and perilous situation. Fly too slowly and the wing stalls because there is not enough air to generate sufficient lift. Fly too fast and the aircraft approaches the speed of sound, where shock waves form and control becomes unpredictable and dangerous. As altitude increases, these two limits converge until they nearly meet, leaving only a narrow corridor of safe speeds between them. This region is called the coffin corner, a name that captures its deadly seriousness. Pilots flying at the edge of the atmosphere must hold their speed within this shrinking margin, where a gust of wind or a moment of inattention can push the aircraft into either danger. It is the price of flying higher than aircraft were designed to fly. And from the dangerous edges of flight, we now glide into the quiet physics of how wings bend and flex. Aircraft wings are designed to flex, sometimes bending several meters upward in turbulence without breaking. The wings of a modern airliner are not rigid beams, but carefully engineered structures designed to bend and flex under load. In severe turbulence, wingtips may rise several meters above their resting position, and this flexibility is not weakness but strength. A rigid wing would concentrate stress at specific points and eventually crack, while a flexible wing distributes load across its entire structure, absorbing energy like a bow being drawn. The materials and architecture of modern wings have been tested to withstand forces far beyond anything encountered in normal flight, bent and twisted in laboratories, until engineers understand where the limits lie. Passengers sometimes worry when they see wings bouncing in rough air, but what they are witnessing is physics working exactly as designed. The wing bends so that the aircraft does not break. Flutter is a deadly oscillation that can destroy an aircraft if its wings resonate at the wrong frequency. Every structure has natural frequencies at which it prefers to vibrate, like a tuning fork ringing at a particular pitch. When airflow over a wing excites one of these frequencies, the wing begins to oscillate, and if the energy from the airflow matches the energy being dissipated, the oscillation grows larger with each cycle until the structure tears itself apart. This phenomenon is called flutter, and it can destroy an aircraft in seconds. Engineers spend years designing wings to ensure flutter does not occur within the flight envelope, testing scale models and running simulations to identify dangerous frequencies. Stiffening certain parts of the wing, adding mass in strategic locations, and shaping control surfaces can all shift the flutter boundary to speeds the aircraft will never reach. Flutter is the silent terror aeronautical engineers must always keep at bay. Wind tunnel testing allows engineers to study airflow around models before building full-size aircraft. Before any new aircraft takes to the sky, its shape has been tested countless times in wind tunnels, those long chambers where fans drive air over scale models, while instruments measure every force and pressure. Wind tunnels allow engineers to see problems before they become dangerous, to refine shapes for efficiency, to understand how an aircraft will behave in conditions too risky to test in real flight. The models are mounted on sensitive balances that measure lift, drag, and side forces, while smoke or lasers reveal the invisible patterns of airflow. Modern wind tunnels can simulate the thin air of high altitude or the crushing pressures of supersonic flight. Every major aircraft in history has spent countless hours in these artificial atmospheres before its first flight. The wind tunnel is where ideas meet reality in a controlled collision. Computational fluid dynamics now simulates millions of airflow interactions in ways no wind tunnel could replicate. Computers have transformed the way engineers understand aerodynamics. Computational fluid dynamics divides the air around an aircraft into millions of tiny cells and calculates how each cell influences its neighbors, tracking pressure, temperature, and velocity as the flow evolves. These simulations reveal details no wind tunnel can capture, visualizing the formation of vortices, the transition from laminar to turbulent flow, the precise location where shocks form at supersonic speeds. Supercomputers can simulate entire flights, testing aircraft in virtual storms at altitudes where physical models cannot survive. Yet computational methods complement rather than replace wind tunnels, because every simulation must be validated against reality. The mathematics of fluid flow is elegant but complex. Even computers struggle to capture every nuance of air in motion. The Reynolds number is a dimensionless quantity that predicts whether airflow will be laminar or turbulent. In the early 20th century, Osborne Reynolds discovered that the behavior of flowing fluids could be predicted by a single number, a ratio that combines velocity, length, and viscosity into a dimensionless quantity. At low Reynolds numbers, flow remains smooth and orderly, each layer sliding past its neighbor in the laminar regime. At high Reynolds numbers, the flow becomes turbulent, chaotic, and energetically expensive. The Reynolds number explains why the same wing design that works beautifully on a model aircraft may behave differently at full scale. It allows engineers to translate wind tunnel results to real aircraft and to understand why insects, birds, and jets all experience the air in fundamentally different ways. It is one of those rare numbers that compresses complex physics into a single, powerful insight. Sometimes understanding begins with a ratio. Insects fly in a different aerodynamic regime than birds or aircraft because of their small size and slow speeds. At the scale of a bee or a mosquito, air feels thick and syrupy, almost like swimming through honey. The Reynolds numbers are so low that the aerodynamic rules that govern aircraft barely apply. Insects cannot rely on conventional lift alone, but instead use complex wing motions, rotating their wings at the end of each stroke to generate vortices that provide extra force. Their flight is a constant battle against viscosity, each wing beat pushing against air that seems reluctant to move. This is why insect wings beat so rapidly, hundreds of times per second, and why even small changes in wing shape can have dramatic effects on performance. Scientists study insect flight not just from curiosity, but because understanding these tiny flyers may inspire new kinds of micro-aircraft. Nature solved aerodynamic problems long before engineers dreamed of flight. And from the smallest flyers, we rise to the giants that cross continents at the edge of the atmosphere. The Boeing 747 was designed to fly higher and faster than any previous commercial aircraft. When the Boeing 747 first flew in 1969, it was the largest passenger aircraft the world had ever seen, a giant capable of carrying hundreds of passengers across oceans in a single leap. Its distinctive hump, housing the cockpit and an upper passenger deck, became one of the most recognizable silhouettes in aviation. The 747 cruises at around 900 kilometers per hour at altitudes above 10,000 meters, high in the lower stratosphere where the air is smooth and fuel consumption is optimized. For decades, it defined what long-distance air travel meant, opening routes that had been impossible before and shrinking the world in ways that changed how humanity thinks about distance. Though newer and more efficient aircraft have since appeared, the 747 remains an icon. It taught the world that oceans are merely inconveniences, not barriers. The Concorde flew at twice the speed of sound, crossing the Atlantic in under 3.5 hours. For 27 years, the Concorde represented the pinnacle of commercial aviation, a needle-nosed dart that cruised at Mach 2, twice the speed of sound, carrying passengers from London to New York in about 3 hours. At that speed, the aircraft's aluminum skin heated to over 100 degrees from friction with the air, and the fuselage expanded several centimeters during flight. The Concorde flew so high, at nearly 18,000 meters, that passengers could see the curvature of the Earth and the darkness of space above. It was loud, expensive, and consumed enormous quantities of fuel, but it offered something no other aircraft could: the ability to arrive before you left, crossing time zones faster than the sun. The Concorde retired in 2003, but its legacy endures. For a brief moment, humanity truly conquered time and distance. Supersonic flight creates shock waves that compress air violently, producing the sonic boom heard on the ground. When an aircraft exceeds the speed of sound, it can no longer push air smoothly aside because sound waves, which normally carry pressure information ahead of the aircraft, cannot outrun it. Instead, pressure changes pile up into a sudden, violent discontinuity called a shock wave, a wall of compressed air that trails behind the aircraft like the wake of a boat. When this shock wave reaches the ground, it arrives as a sharp crack known as a sonic boom, sometimes strong enough to rattle windows and startle animals. The boom is not a single event at the moment of breaking the sound barrier, but a continuous phenomenon that follows the aircraft throughout its supersonic flight. Supersonic travel over land has been banned in many countries because of the disturbance these booms cause. Speed has consequences that reach all the way to the ground. The sound barrier is not a physical wall, but a region of rapidly increasing drag as an aircraft approaches the speed of sound. In the early days of high-speed flight, pilots spoke of a wall in the sky, an invisible barrier that no aircraft could cross. As aircraft approached the speed of sound, drag increased dramatically, controls became unpredictable, and several test pilots died in violent structural failures. The sound barrier seemed impenetrable until Chuck Yeager, in 1947, flew the rocket-powered Bell X-1 faster than sound and proved that the barrier was not a wall but a transition. The region around Mach 1 is called the transonic regime, where some parts of the airflow are subsonic and others supersonic, creating complex interactions that stress both aircraft and pilots. Once through this turbulent zone, flight actually becomes smoother again. The barrier was never a wall, only a frontier. Frontiers are made to be crossed. Mach number is the ratio of an object's speed to the speed of sound in the surrounding air. When engineers speak of high-speed flight, they rarely talk in kilometers per hour, but instead use a number named after the Austrian physicist Ernst Mach. The Mach number expresses velocity as a fraction of the speed of sound. So Mach 1 means flying at the speed of sound, Mach 2 means twice that speed, and so on. This ratio matters because physics changes dramatically as you approach and exceed the speed of sound, with shock waves forming, drag spiking, and lift behaving in unexpected ways. At sea level, the speed of sound is about 1,200 kilometers per hour, but at cruising altitude, where air is colder, it drops noticeably. Pilots must always know their Mach number because the limits of their aircraft are defined not by fixed speeds, but by how fast they are flying relative to sound. Speed is relative to the medium. The speed of sound decreases at higher altitudes because sound travels slower through colder air. Sound is a vibration that travels through air by molecules bumping into one another, and the speed at which this chain reaction propagates depends on how fast those molecules are moving. In warm air, molecules vibrate more energetically and collide more frequently, so sound travels faster. In the cold air of the stratosphere, where temperatures can drop to -50 degrees or more, molecules move sluggishly, and sound slows to around 1,000 kilometers per hour. This is why an aircraft flying at the same indicated speed can be subsonic at low altitude, but approach the speed of sound at high altitude, where the threshold is lower. Pilots climbing to cruise must watch their Mach number carefully as the sound barrier descends toward them. The invisible line moves as the temperature changes, and the physics adjusts accordingly. And from the speed of sound, we turn to the silent world of gliding, where engines fall quiet and only air provides lift. A glider can stay aloft for hours without an engine by riding columns of rising air called thermals. When sunlight heats the ground unevenly, pockets of warm air break free from the surface and rise like invisible bubbles through the cooler air above them. These rising columns are called thermals, and glider pilots learn to find them by watching for circling birds, by feeling the subtle changes in airspeed, by seeing cumulus clouds forming at their tops where the moisture condenses. Once inside a thermal, the glider circles tightly, climbing hundreds of meters in minutes without burning a single drop of fuel. From there, the pilot glides toward the next thermal, trading altitude for distance, rising and gliding across landscapes using nothing but the energy of the sun. It is flight distilled to its purest form, an intimate partnership between pilot and atmosphere. The sky gives lift freely to those who know how to ask gently. Thermal soaring is the art of spiraling upward inside bubbles of warm air rising from sun-heated ground. Thermal soaring requires patience, skill, and an almost instinctive feel for the invisible currents of air moving all around the sky. The pilot enters a thermal and turns tightly, keeping the rising core perfectly centered as the altimeter climbs steadily upward toward the clouds above. Outside the thermal, air sinks, so precise positioning matters enormously. Experienced pilots can feel the thermal through their sensitive controls, sensing which way to turn by the subtle lift under one wing or the sink under another. On good days, thermals line up like stepping stones across the landscape, and a skilled pilot can travel hundreds of kilometers without ever starting an engine. It is a form of flight that connects human and nature more intimately than any powered aircraft ever could. There is only silence, and there is lift. Ridge lift occurs when wind strikes a hillside and is deflected upward, creating a band of rising air along the slope. When steady wind flows toward a hill or mountain, it has nowhere to go but up, and the air that rises along the windward slope can provide continuous lift for gliders flying along the ridge below the clouds. Unlike thermals, which are scattered and unpredictable, ridge lift is reliable and steady, a river of rising air that follows the contour of the terrain below. Pilots can fly back and forth along a ridge for hours, barely losing altitude, covering enormous distances if the ridge extends far enough across the landscape. Some of the longest glider flights in history have used ridge lift, following mountain ranges for many hundreds of kilometers. It is a simpler form of soaring than thermal hunting, more meditative, more predictable. The mountain does the work while the pilot follows the contour of the earth. Wave lift can carry gliders to altitudes above 40,000 feet, using standing waves in the atmosphere. When strong winds blow over mountain ranges, they can set up patterns of oscillation that extend deep into the atmosphere, creating standing waves that rise and fall in place like ripples frozen in the sky above the peaks. Gliders that find the rising portion of these waves can climb to extraordinary altitudes, far higher than any thermal or ridge lift could carry them, into the cold, thin air where commercial jets cruise far above the earth. The current altitude record for a glider is over 23,000 meters, reached using wave lift, altitudes so extreme that pilots must wear pressure suits and breathe supplemental oxygen to survive. These flights take gliders to the edge of space without a single engine, powered only by the interaction of wind and mountain. The atmosphere holds energy waiting to be borrowed. The albatross can glide for hours without flapping its wings, using a technique called dynamic soaring. The wandering albatross circles the Southern Ocean for years at a time, rarely ever touching land, its enormous wings extended in flight that seems almost effortless and eternal in the wind. The secret is a technique called dynamic soaring, which exploits the difference in wind speed between the slow air near the water surface and the faster-moving air just a few meters above it. The albatross dives toward the waves, gaining speed, then turns and climbs into the stronger, faster wind, converting that speed difference into precious altitude and forward momentum. By repeating this cycle endlessly, the bird extracts energy from the wind without ever flapping its powerful wings. It is flight powered by gradient, by the subtle physics of shear. The albatross has mastered an art that engineers are only now beginning to understand. Dynamic soaring exploits the difference in wind speed between layers of air close to the ocean's surface and higher up. Near any surface, whether ocean, desert, or open grassland, friction slows the wind, creating a gradient where air moves faster at height than at ground level below. Dynamic soaring extracts energy from this gradient by flying loops that cross between the slow and faster layers of moving air. As the bird or glider climbs into faster air, it gains energy without any real effort, like a surfer catching a powerful wave. Model aircraft pilots have used this technique to achieve speeds exceeding 700 kilometers per hour, powered by nothing but wind shear. The physics is subtle and the timing must be perfectly precise, but the reward is flight that costs nothing, sustained indefinitely by the energy already present in the moving atmosphere. It is perpetual motion, borrowed from the gradient of the wind. Glide ratio measures how far an aircraft can travel horizontally for every unit of altitude lost. Every aircraft that lacks thrust is slowly falling, trading altitude for forward motion, and the efficiency of this trade is captured by a number called the glide ratio. A commercial airliner might glide 15 meters forward for every meter it descends, giving it a glide ratio of 15:1, enough to reach a distant runway in an emergency. A high-performance sailplane can achieve ratios of 60:1 or even better, covering enormous distances while barely sinking at all. The glide ratio depends on the shape of the aircraft, its weight, its airspeed, and the configuration of its control surfaces. At the optimal speed, lift is maximized relative to drag, and the aircraft floats forward with minimal loss. Pilots memorize these numbers because in an emergency, the glide ratio defines exactly how far they can travel. A modern sailplane can glide over 60 kilometers while losing only a single kilometer of altitude. The most efficient sailplanes ever built achieve glide ratios of more than 60:1, numbers that seem almost magical when you consider that no engine is involved in keeping them aloft in the sky. These aircraft are marvels of aerodynamic refinement, with long, slender wings that minimize induced drag and surfaces polished until they are smoother than glass. Every single rivet, every seam has been engineered away to keep the boundary layer laminar across the entire span. From an altitude of 1 kilometer, such a sailplane could glide 60 kilometers or more in still air, enough to cross small countries without losing much height. In the hands of a skilled pilot using thermals and ridge lift, hundreds of kilometers become possible in a single day. It is flight reduced to mathematics, where shape and air do all the work. And as these thoughts of invisible forces drift through your mind, let your breathing become slow and steady, like a glider circling gently in a thermal. There is no effort needed, only the quiet rise and fall of air carrying you toward rest. This is sleepy science, gentle facts to fall asleep to. Birds sense air pressure changes through specialized receptors and adjust their flight accordingly. Embedded within a bird's skull and along its wing bones are tiny sensory organs called baroreceptors that detect even the smallest shifts in atmospheric pressure. These biological pressure sensors allow birds to feel an approaching storm hours before it arrives, to sense the subtle pressure drop over a rising thermal, to detect the compression of air against their feathers during a steep dive. When pressure changes, the bird's nervous system responds instantly, adjusting wing beat and angle to maintain control. This sensitivity is so refined that some species can navigate by pressure gradients alone, reading the atmosphere like a map written in invisible ink. It is an awareness that humans must build complex instruments to achieve, yet birds are born with it. The sky speaks in pressure, and every bird understands the language. Feathers are among the most aerodynamically efficient structures ever evolved by nature. Each feather is a miracle of natural engineering, a structure so light that it weighs almost nothing, yet so strong that it can withstand the forces of high-speed flight and tight maneuvering. The central shaft provides rigidity while the barbs and barbules interlock to create a smooth, continuous surface that guides air with minimal turbulence and drag. Feathers can flex and twist under load, adapting their shape to changing conditions, something no human-made material can quite replicate. When damaged, they simply molt and regrow, a self-repairing system that engineers can only dream of imitating. The overlapping arrangement creates a seamless wing surface that rivals any aircraft skin in aerodynamic efficiency. Millions of years of evolution have refined feathers into the perfect flight material, light and strong and beautiful. The alula is a small cluster of feathers on a bird's thumb that acts like a leading-edge slat to prevent stalling. At the bend of a bird's wing, where the human thumb would be, sits a small cluster of stiff feathers called the alula that can be extended like a tiny auxiliary wing. When a bird approaches a stall, at slow speeds or high angles of attack, it extends the alula forward to create a gap that channels fast-moving air over the main wing surface, energizing the boundary layer and delaying separation. This is exactly the principle that engineers use in leading-edge slats on commercial aircraft, a solution that evolution discovered millions of years before the first airplane flew. Watch a bird landing on a branch and you will see the alula pop out as the wings angle steeply, keeping airflow smooth until the final moment. It is stall prevention built into biology, elegant and automatic. The bird adjusts without thinking, guided by instinct refined over countless generations. Hummingbirds generate lift on both the upstroke and the downstroke of their wings, unlike most other birds. Most birds fly by pushing down against the air and then recovering their wings on the upstroke, but the hummingbird has evolved a different approach that allows it to hover motionless in front of a flower. By rotating its wings in a figure-of-8 pattern and generating lift on both strokes, the hummingbird produces continuous upward force without any forward motion at all. This requires extraordinary muscular control and an extremely high wing beat frequency, sometimes exceeding 80 beats per second in smaller species. The metabolic cost is enormous, which is why hummingbirds must feed constantly on energy-rich nectar throughout every waking hour. Their flight muscles can make up a third of their body weight, a proportion unmatched by any other bird. It is flight taken to an extreme, hovering perfected through evolutionary time. The peregrine falcon can exceed 300 kilometers per hour in a hunting dive called a stoop. When a peregrine falcon spots prey far below, it folds its wings close to its streamlined body and enters a near-vertical dive called a stoop, accelerating faster than any other creature on Earth. Wind tunnel studies have measured stoop speeds exceeding 380 kilometers per hour, making the peregrine the fastest animal alive by a considerable margin. Special baffles in its nostrils prevent the rush of air from damaging its lungs, while a third eyelid protects its eyes from drying out at such extreme velocity. At the bottom of the dive, the falcon opens its wings and strikes its prey with clenched talons, the impact often killing instantly through the transfer of kinetic energy. This is hunting perfected over millions of years, aerodynamics and predation fused into a single deadly moment of pure precision. And from the fastest hunters in the sky, we descend to the physics of how aircraft slow down and land. Flaps extend from the trailing edge of a wing to increase lift and drag during landing. As an aircraft prepares to land, it must slow down while maintaining enough lift to stay airborne on the approach, and flaps make this possible by changing the shape of the wing. When extended, flaps increase both the curvature and the surface area of the wing, producing more lift at lower speeds but also increasing drag. This allows the aircraft to descend at a steeper angle without accelerating, essential for landing at airports surrounded by obstacles or in valleys. Different flap settings are used for different phases, from a partial extension during approach to full deployment just before touchdown. The mechanical systems that deploy flaps must be extremely reliable, since failure could leave the aircraft unable to slow down safely. Flaps transform the wing from a cruising shape into a landing shape, adapting to the needs of the moment. Slats extend from the leading edge and help maintain smooth airflow at high angles of attack. At the front of an aircraft wing, slats can be extended forward and downward to create a slot through which high-energy air flows onto the upper wing surface. This energizes the boundary layer and prevents airflow separation at the high angles of attack necessary for slow-speed flight during landing and takeoff. Without slats, a wing would stall at much higher speeds, requiring longer runways and more dangerous approach profiles. Modern aircraft deploy slats automatically when flaps are extended, the two systems working together to reconfigure the wing for low-speed operations. The slot effect was discovered in the early days of aviation and remains one of the most important solutions to the challenge of slow-speed flight. Slats allow wings designed for efficient cruise to also perform at the slow speeds needed to land safely on relatively short runways. Spoilers disrupt the airflow over a wing, reducing lift and increasing drag to help slow the aircraft. Mounted on top of the wing, spoilers are flat panels that can hinge upward into the airflow, breaking up the smooth flow over the wing surface and dramatically reducing lift while increasing drag. During landing, spoilers deploy immediately after touchdown to dump lift and press the wheels firmly onto the runway, ensuring that the brakes can grip effectively. In flight, spoilers can be used asymmetrically for roll control, or symmetrically to steepen a descent without increasing airspeed. Some aircraft use spoilers as speed brakes, deploying them partially to slow down when approaching a faster aircraft ahead or when descending from cruise altitude. The name says it all. Spoilers spoil the clean airflow that generates lift, turning aerodynamic elegance into deliberate turbulence. They are crude compared to other control surfaces, but their effectiveness is undeniable. Reverse thrust redirects engine exhaust forward to help decelerate an aircraft after landing. Jet engines are designed to push air backward, accelerating the aircraft forward, but during landing this thrust can be redirected using clamshell doors or deflectors that send the exhaust stream forward. This reverse thrust creates a powerful braking force that supplements the wheel brakes, especially important on wet or icy runways where braking friction is reduced. The roar that passengers hear just after touchdown is often the sound of thrust reversers deploying, their loud and distinctive rumble announcing that the landing roll has begun. Not all the thrust is truly reversed. Much of it is simply deflected sideways, but the effect on deceleration is still dramatic. Pilots must deactivate reverse thrust before the aircraft slows too much, or the redirected exhaust could be sucked back into the engines. It is power turned backward, momentum canceled by its own source. Ground effect provides a cushion of extra lift when an aircraft flies very close to the surface. When an aircraft flies very close to the ground, within a wingspan of the surface, the downwash from the wings is disrupted by the earth below, reducing induced drag and creating a cushion of extra lift. This phenomenon is called ground effect, and pilots feel it as a floating sensation just before touchdown, as though the aircraft does not want to settle onto the runway. The same effect occurs during takeoff, allowing heavily loaded aircraft to lift off at lower speeds than they could achieve without the ground nearby. Some experimental craft have been designed to fly in ground effect, skimming across water or flat terrain with remarkable efficiency. The physics involves the reflection of wingtip vortices and the compression of air beneath the wing, creating a pocket of enhanced lift. It is the Earth lending a hand in those final moments of descent. And from the moment of touchdown, we rise again to explore the invisible highways of the jet stream. The jet stream is a river of fast-moving air that flows around the planet at high altitude. High above the surface, where the troposphere meets the stratosphere, narrow bands of fast wind circle the Earth like invisible rivers flowing through the sky. These are the jet streams, currents of air that can reach speeds of over 300 kilometers per hour, driven by the temperature difference between tropical and polar air masses. The jet stream meanders north and south like a river on a floodplain, its position shifting with the seasons and with complex atmospheric dynamics. Aircraft that enter these currents feel the rush of wind pushing them along, either speeding their journey or fighting against their progress depending on direction. The jet stream was first discovered by high-altitude pilots during the Second World War who found themselves flying backward despite full throttle. It is a highway in the sky, invisible but powerful. Aircraft flying with the jet stream can save hours of fuel and time on transcontinental journeys. Airlines plan their routes carefully to take advantage of the jet stream when flying eastward and to avoid it when flying west. A flight from Los Angeles to London might take 2 hours less than the return journey simply because of the strong tailwind provided by the jet stream pushing the aircraft along. Over a year, this difference adds up to enormous savings in fuel, time, and cost for airlines flying transcontinental and transoceanic routes. Flight planners study weather data every single day to find the optimal altitude and path that will catch the strongest tailwind or avoid the worst headwind. Sometimes the most fuel-efficient route is not the shortest distance, but a longer curve that rides the jet stream like a surfer riding a wave. It is navigation shaped by invisible rivers of wind flowing high above the clouds. Clear air turbulence occurs in the jet stream without any visible clouds to warn pilots. At the edges of the jet stream, where fast-moving air meets slower air, wind shear can create violent turbulence without any clouds to mark its presence. This is called clear air turbulence, and it is one of the most unpredictable hazards of high-altitude flight because it cannot be seen on radar or from the cockpit. Passengers experience it as sudden jolts and drops, moments when the aircraft lurches without warning as it crosses invisible boundaries in the atmosphere. Pilots rely on reports from other aircraft, on satellite data, and on computer models to predict where clear air turbulence might occur, but surprises still happen. Modern LiDAR systems can detect turbulence ahead by measuring changes in air density, giving pilots precious seconds to slow down and warn passengers. Until then, the fasten seatbelt sign remains the best protection against the invisible chaos of the jet stream. The polar vortex is a mass of cold air that circulates around the poles and affects weather patterns far below. Surrounding each pole is a vast swirling mass of extremely cold air held in place by a ring of strong winds called the polar vortex. When the vortex is stable, the cold air stays trapped near the pole, but when it weakens or wobbles, lobes of frigid air can break away and plunge southward, bringing sudden blasts of winter cold to regions far from the Arctic. Aircraft flying polar routes must account for these atmospheric patterns, both for the extreme cold that affects engine performance and for the turbulence that can occur at the boundaries of cold and warm air. Climate change is affecting the stability of the polar vortex, making sudden cold outbreaks more frequent and less predictable in some years. High above, the vortex spins endlessly, a sentinel of cold air visible only to satellites and weather instruments. It is winter's engine, hidden at the top of the world. Mountain waves can propagate upward into the stratosphere, creating turbulence far from any visible terrain. When strong winds blow over mountain ranges, the disturbance does not stop at the peaks, but continues upward in waves that can extend into the stratosphere. These mountain waves create alternating bands of rising and sinking air that extend far downwind of the terrain, sometimes hundreds of kilometers away. Aircraft flying through mountain waves encounter turbulence that seems to come from nowhere, far from any visible mountains, catching pilots by surprise. The most violent mountain wave turbulence occurs in the rotors beneath the wave crests, zones of chaotic spinning air that can flip small aircraft or damage larger ones. Satellite images sometimes show long parallel cloud bands called lenticular clouds, marking the presence of mountain waves below. It is the mountain's reach extending invisibly into the high atmosphere. Cumulonimbus clouds can tower above 40,000 feet, forcing aircraft to navigate around them. The tallest thunderstorm clouds, called cumulonimbus, can punch through the troposphere and tower into the stratosphere, reaching heights that dwarf even the cruising altitude of jets. Inside these giants are violent updrafts and downdrafts, hail, lightning, and turbulence so severe that it can damage aircraft structures. No pilot willingly enters a cumulonimbus cloud, instead navigating around them using weather radar that paints the densest precipitation in angry red and orange colors. The supercooled water droplets inside can freeze instantly onto wings and engines, adding dangerous weight and disrupting airflow. At night, the internal lightning illuminates these clouds from within, creating dramatic displays visible from hundreds of kilometers away. They are the atmosphere at its most violent, columns of energy that demand respect from everyone who flies. And from the storms that aircraft avoid, we turn to the materials that keep them strong and light. The strength-to-weight ratio of an aircraft material determines how much it can carry and how far it can fly. Every kilogram of material used in an aircraft structure is a kilogram that cannot be used for passengers, cargo, or fuel. So engineers seek materials that are as strong as possible while weighing as little as possible. The strength-to-weight ratio measures how much load a material can bear relative to its mass, and improvements in this ratio have driven aviation from wood and fabric through aluminum to composites. A material that is twice as strong but weighs the same can carry twice the load, or the same load with a lighter, more fuel-efficient design. The quest for better ratios has led engineers to develop alloys, composites, and structures that would have seemed like science fiction a century ago. Every new material represents decades of research and refinement. It is the arithmetic of flight, where weight is the enemy of performance. Aluminum alloys dominated aircraft construction for decades, because of their combination of lightness and strength. For most of aviation history, aluminum alloys have been the material of choice for aircraft construction, offering an excellent balance of strength, lightness, and workability that no other metal could match. Pure aluminum is too soft for structural use, but when alloyed with copper, magnesium, zinc, and other elements, it becomes strong enough to bear the loads of flight while remaining light enough to fly. Aluminum does not rust like steel. It can be formed into complex shapes, and it can be riveted, welded, or bonded as needed. Generations of engineers have learned to design with aluminum, developing techniques for predicting its behavior under every condition of stress and fatigue. Even today, many aircraft are still built from aluminum alloys, a testament to the material's versatility. It is metal shaped for flight, proven over a century. Carbon fiber composites are now replacing aluminum in many modern aircraft because they are even lighter and stronger. Carbon fiber composites consist of thin strands of carbon woven into fabric and embedded in a plastic resin that hardens into a material stronger than steel, but weighing a fraction as much. The fibers can be oriented to provide strength exactly where it is needed, allowing engineers to create structures that are both lighter and more efficient than anything possible with metal. Composites do not corrode like aluminum, they resist fatigue better, and they can be molded into complex aerodynamic shapes without the joints and rivets that metal requires. The manufacturing process is complex and expensive, but the fuel savings over the life of an aircraft more than compensate. Modern aircraft wings flex and twist in flight, and composites handle this better than metal ever could. It is strength woven from carbon threads. The Boeing 787 Dreamliner is made of more than 50% composite materials by weight. When Boeing designed the 787 Dreamliner, they made a bold decision to build the fuselage and wings primarily from carbon fiber composites rather than aluminum. More than half the aircraft's structure by weight is composite, a proportion unmatched by any previous commercial airliner. This allows the 787 to be lighter and more fuel efficient than comparable aircraft, while also permitting larger windows and higher cabin pressure that make passengers more comfortable. The composite fuselage is built in large barrel sections that are joined together, eliminating thousands of metal fasteners that would have been needed with aluminum. Manufacturing the 787 required new factories and techniques that Boeing had to invent along the way. It is a flying demonstration that composites have come of age, pointing the way toward the aircraft of the future. Metal fatigue can cause tiny cracks to grow in aircraft structures over thousands of flight cycles. Every time an aircraft takes off and lands, its structure flexes under the changing loads of flight, and over thousands of cycles, these tiny movements can cause microscopic cracks to form in the metal. At first, the cracks are invisible, far too small to detect, but with each flight they grow a little larger, spreading through the material until they reach a critical size. This is metal fatigue, and it has caused tragic accidents in aviation when undetected cracks suddenly failed. Modern aircraft undergo rigorous inspection schedules to catch these cracks before they become dangerous, using techniques like ultrasound and X-ray that can see what the eye cannot. Engineers also design structures with multiple load paths, so if one part fails, others can carry the load. It is a constant battle against the invisible growth of cracks, where vigilance is the price of safety. Pressurization cycles stress an aircraft fuselage, like a balloon being inflated and deflated repeatedly. When an aircraft climbs to cruising altitude, the cabin is pressurized to create a comfortable environment for passengers despite the thin air outside, and this pressure pushes outward on the fuselage like air inside a balloon. Each landing depressurizes the cabin, and each takeoff pressurizes it again, a cycle that repeats thousands of times over the life of an aircraft. This constant inflation and deflation stresses the skin and structural joints, creating perfect conditions for fatigue cracks to grow. The comet disasters of the 1950s were caused by fatigue cracks at the corners of square windows, teaching engineers to use rounded shapes that spread stress evenly. Modern aircraft are designed with these lessons in mind, using reinforced structures and careful stress analysis. Every pressurization cycle is a small assault on the airframe, counted and accounted for. And from the stresses hidden within aircraft structures, we gaze outward to the silence of even higher flight. The U-2 spy plane cruises at over 20,000 meters, where the sky turns dark and stars become visible. The U-2 spy plane was designed to fly so high that it would be beyond the reach of Soviet missiles and fighters, cruising at altitudes where the sky above fades from blue to nearly black. At over 20,000 meters, the air is so thin that the margin between stalling and overspeed becomes razor thin, a region pilots call the coffin corner because both limits are dangerously close. Pilots wear full pressure suits like astronauts, breathing pure oxygen and protected against the near vacuum outside. The view from the cockpit is like no other, with the curve of the Earth visible and stars appearing even during daylight. These aircraft still fly today, gathering atmospheric data and performing reconnaissance that satellites cannot match. It is flight at the edge of space, where the atmosphere whispers its final breath. At extreme altitude, pilots must wear pressure suits because the cabin cannot be pressurized enough. Above a certain altitude, the atmosphere becomes so thin that even the most powerful pressurization systems cannot maintain a safe cabin environment, so pilots must wear pressure suits that create their own sealed atmosphere. These suits are essentially personal spacecraft, providing oxygen, temperature regulation, and protection against the vacuum-like conditions outside. The suits are bulky and restrictive, making the already demanding task of flying even more challenging, yet they are essential for survival. If the suit or the cabin loses pressure at extreme altitude, a pilot has only seconds before losing consciousness and minutes before death. Every flight at these heights is a careful dance with the limits of human endurance and engineering capability. The pressure suit is the final barrier between pilot and the hostile void of near space. The SR-71 Blackbird flew so fast that its titanium skin expanded several inches during flight due to friction heating. The SR-71 Blackbird remains the fastest air-breathing aircraft ever flown, capable of cruising at over 3 times the speed of sound, where friction generates temperatures that would melt conventional aluminum. The aircraft was built primarily from titanium, a metal that retains its strength at high temperatures, but was extremely difficult to work with at the time. On the ground, the Blackbird actually leaked fuel from its joints because the panels were designed to fit tightly only when expanded by heat in flight. At cruising speed, the airframe would grow several inches longer as the metal expanded, a transformation that engineers had to account for in every aspect of the design. The Blackbird was retired decades ago, but nothing since has matched its combination of speed and altitude. It was speed made visible, a streak of dark metal against the stratosphere. And as you drift deeper into rest, imagine the silence that surrounds an aircraft at the edge of space, where the air is so thin that sound can barely travel. Let that stillness settle over you now, like a documentary for sleep carrying you into deep sleep. Hypersonic flight occurs at speeds greater than 5 times the speed of sound, where aerodynamics becomes dominated by heat. Beyond Mach 5, the physics of flight changes dramatically as aerodynamic heating becomes the dominant challenge, with surfaces reaching temperatures that can melt most metals. This is hypersonic flight, a realm where the air itself begins to break apart into plasma and where traditional aerodynamic shapes no longer work as expected. Shock waves wrap tightly around the vehicle, creating zones of extreme pressure and heat that must be carefully managed to prevent destruction. The vehicles that fly at these speeds look different from conventional aircraft, with blunted noses and swept-back shapes designed more for heat management than for lift. Only a handful of experimental vehicles have achieved sustained hypersonic flight, each one representing decades of research. It is a frontier where heat itself becomes the enemy, and survival depends on understanding fire. Scramjet engines can only ignite at hypersonic speeds, breathing supersonic air without slowing it down first. Conventional jet engines compress incoming air and slow it below the speed of sound before mixing it with fuel and igniting it. But at hypersonic speeds, this process wastes enormous amounts of energy. Scramjets solve this problem by allowing the air to flow through the engine at supersonic speeds throughout, compressing and igniting it without ever slowing it down. The challenge is that scramjets cannot start from rest. They must already be moving at several times the speed of sound before ignition is even possible. Experimental scramjet vehicles have been launched from rockets or dropped from high-flying aircraft to achieve the necessary starting speed for the engines to light. Once running, a scramjet can theoretically propel a vehicle to orbital velocities using only air and fuel. It is an engine that feeds on speed itself. The space shuttle re-entered the atmosphere at over 25 times the speed of sound, protected by heat-resistant tiles. When the space shuttle returned from orbit, it entered the atmosphere at speeds exceeding 25 times the speed of sound, generating temperatures that would incinerate unprotected metal in moments. The underside of the orbiter was covered with thousands of silica tiles, each one custom-fitted to its exact location, designed to absorb and radiate heat without transferring it to the aluminum structure beneath. These tiles were so effective at insulating that one side could glow red-hot while the other remained cool enough to touch. The shuttle's re-entry created a long trail of ionized air as it slowed, a streak of fire visible from the ground below. Every return was a controlled fall through fire, trusting materials and mathematics to bring the crew home safely. It was flying at the speed of meteors, wrapped in a shell of ceramic glass. Ablative heat shields protect spacecraft by slowly burning away and carrying heat with them. Some spacecraft use a different approach to surviving re-entry heat, covering themselves in materials designed to slowly burn away and carry the enormous thermal energy with them as they vaporize. These ablative heat shields work by sacrificing themselves, converting the intense heat of re-entry into the latent energy needed to transform solid material into gas. As the outer layer burns away, it carries hot gases with it and creates a protective barrier that keeps the heat from reaching the spacecraft safely beneath. The Apollo capsules used ablative shields to survive their fiery returns from the moon, and modern crew capsules continue to rely on the same fundamental principle today. The shield arrives thick and leaves thin, its mass traded for the survival of those inside. It is protection through sacrifice, material giving itself so that the crew may live. The Kármán line at 100 kilometers altitude is the internationally recognized boundary between atmosphere and space. At 100 kilometers above the Earth's surface, an invisible boundary separates atmosphere from space, named for the engineer Theodor von Kármán, who calculated that at this altitude the air becomes too thin for aerodynamic flight. Above the Kármán line, wings no longer generate meaningful lift in vehicles, must rely on reaction propulsion to maneuver and orbital mechanics to stay aloft. This is the threshold that defines astronauts from pilots, space from sky, where the rules of flight give way to the rules of orbit. The boundary is arbitrary in some sense, since the atmosphere fades gradually rather than ending abruptly, but it provides a useful legal and scientific definition. Crossing this line remains one of humanity's great achievements, a testament to our refusal to accept limits. It is the edge of sky where wonder begins. And from the edge of space, we return to the quiet principles that govern every wing and every feather. Camber is the curvature of a wing's cross-section, and it determines how efficiently the wing generates lift. If you slice a wing from leading edge to trailing edge and look at the cross-section, you will see a shape that curves more on top than on bottom, and this asymmetry is called camber. The curvature forces air traveling over the top to move faster and at lower pressure than the air beneath, creating the pressure difference that generates lift. More camber means more lift at low speeds, which is why aircraft designed for slow flight have wings with pronounced curvature, while high-speed aircraft often have flatter, thinner profiles. Adjustable flaps change the camber of a wing during landing, temporarily increasing curvature to produce more lift at lower speeds. The exact shape of a wing's camber has been refined over a century of testing and calculation. It is the curve that carries passengers and cargo into the sky. A symmetrical wing produces no lift at zero angle of attack, while a cambered wing produces lift even when flying level. A wing with the same curvature on top and bottom, perfectly symmetrical, will produce no net lift when the angle of attack is zero because the pressure distribution is the same on both surfaces. To fly level, such a wing must tilt upward slightly, creating an angle that produces the necessary pressure difference. Cambered wings, however, generate lift even when flying perfectly level because their asymmetry ensures that the top surface always accelerates air faster than the bottom. This is why most aircraft wings are cambered, since generating lift without tilting reduces drag and improves efficiency. Symmetrical wings are used mainly for aerobatic aircraft that need to fly inverted as easily as upright and for helicopter rotor blades. The shape of a wing defines its personality, whether it likes to climb or prefers to stay level. Aspect ratio is the relationship between a wing's span and its chord, affecting efficiency and maneuverability. The aspect ratio of a wing compares its span, the distance from tip, to its average chord, the distance from leading edge to trailing edge. A long, narrow wing has a high aspect ratio, while a short, stubby wing has a low aspect ratio. High aspect ratio wings produce less induced drag because the wingtip vortices that waste energy are smaller relative to the total lift being generated across the entire wing surface. This is why gliders and high-efficiency airliners have long, slender wings that stretch far from the fuselage. Low aspect ratio wings are stronger, lighter, and more maneuverable, which is why fighter jets often have shorter, broader wings capable of aggressive turning. Aspect ratio is one of the first choices an aircraft designer must make, carefully balancing efficiency against structural needs and other demands. High aspect ratio wings are more efficient but less maneuverable, which is why gliders have long, narrow wings. Competition gliders have aspect ratios above 20, meaning their wings are more than 20 times as long as they are wide, allowing them to glide enormous distances on very little altitude. These long wings produce minimal induced drag, extracting maximum lift from every cubic meter of air they pass through. But the same length that makes them efficient also makes them slow to roll and vulnerable to structural stress, so they must be built from strong, lightweight materials and flown with care. Fighter jets, in contrast, might have aspect ratios below 4, sacrificing efficiency for the ability to snap into tight turns and withstand violent maneuvers. Each design represents a different answer to the eternal question of flight: how much efficiency to trade for other qualities. The aspect ratio written in metal and composite defines what the aircraft can do. Swept wings delay the onset of shock waves and allow aircraft to fly faster before encountering compressibility effects. As aircraft approach the speed of sound, shock waves begin to form on the wing surface, creating drag that rises sharply and can make control difficult. Sweeping the wings backward angles them relative to the oncoming airflow, effectively reducing the speed of air across the wing's chord and delaying the formation of these shock waves. Most commercial jets have swept wings for exactly this reason, allowing them to cruise efficiently at high subsonic speeds without encountering severe compressibility effects. The angle of sweep is carefully chosen to balance high-speed efficiency against low-speed handling, since swept wings tend to stall differently than straight wings. When you see an airliner's wings angled backward, you are seeing a solution to the invisible barrier of sound. Sweep is the wing's compromise with the physics of high speed. Delta wings provide stability at supersonic speeds, but require higher landing speeds than conventional wings. The delta wing, shaped like a triangle with no tail, was developed for supersonic flight, where its simple geometry handles shock waves better than conventional swept wings. Delta wings are structurally efficient because the deep chord near the fuselage provides plenty of room for fuel and landing gear, while the thin tips reduce weight. They remain stable at supersonic speeds and can reach very high angles of attack without stalling suddenly, advantages for military aircraft that must maneuver aggressively. The trade-off is that delta wings generate high drag at low speeds, requiring high approach and landing speeds that demand longer runways and precise pilot technique. The Concorde used delta wings to cruise at Mach 2, trading low-speed efficiency for supersonic performance. It is a shape born from the demands of breaking the sound barrier. And from the shapes of wings, we turn to the instruments that help pilots navigate the invisible ocean of air. The pitot tube measures airspeed by comparing the pressure of moving air to the static pressure around it. A small tube protruding from the nose or wing of an aircraft, called a pitot tube, faces directly into the airflow and captures the dynamic pressure of air ramming into its opening. Inside the instrument, this total pressure is compared to the static pressure of the surrounding atmosphere, and the difference between them reveals how fast the aircraft is moving through the air. It is elegantly simple, a principle discovered centuries ago applied to measure speeds that the inventors could never have imagined. Pitot tubes must be kept clear of ice and debris, which is why they are often heated, since a blocked tube can give dangerously wrong airspeed readings. Multiple pitot tubes provide redundancy in case one fails or becomes obstructed. It is speed measured by catching air, the most direct way to know how fast you are flying. An altimeter measures altitude by sensing the decreasing air pressure as an aircraft climbs. As an aircraft climbs higher, the weight of the atmosphere above it decreases, and the air pressure drops in a predictable way. An altimeter is essentially a very precise barometer that measures this pressure and converts it to altitude using a standard model of the atmosphere. By knowing the relationship between pressure and height, pilots can tell how high they are flying even when clouds block the view of the ground. The altimeter must be calibrated to the local atmospheric pressure, which changes with weather, so pilots update the setting frequently based on reports from the ground or from air traffic control. Without accurate altimeters, instrument flight through clouds would be impossible, an aircraft could not safely maintain vertical separation. It is height measured by the weight of air, a column of atmosphere translated into numbers. True airspeed differs from indicated airspeed at high altitude because the thinner air affects the instruments. The airspeed shown on a cockpit dial is called indicated airspeed, and it measures the dynamic pressure of air entering the pitot tube, but at high altitude this reading becomes misleading. Thin air exerts less pressure for the same true speed, so the indicated airspeed drops even though the aircraft is actually moving faster through the air mass. True airspeed accounts for air density and represents the actual velocity of the aircraft relative to the air around it. Pilots must know both numbers, indicated airspeed for handling and stall margins, true airspeed for navigation and timing. Modern flight computers make the conversion automatically, but pilots learn the relationship early because understanding it is essential for safe, high-altitude flight. It is the difference between what the instruments feel and what is actually happening. The artificial horizon shows a pilot the aircraft's orientation when flying through clouds with no external reference. When flying through clouds or at night, pilots cannot see the horizon, and without external reference, the human senses quickly become confused about which way is up. The artificial horizon, also called the attitude indicator, displays a small model of the aircraft against a representation of sky and ground, showing the pilot exactly how the aircraft is pitched and banked. Gyroscopes inside the instrument maintain a stable reference regardless of how the aircraft moves, providing a constant truth in a world where the senses can lie. This instrument has saved countless lives by allowing pilots to maintain level flight when disorientation would otherwise lead them into spirals or stalls. Modern aircraft use electronic displays, but the principle remains the same. It is the pilot's substitute for the natural horizon, a mechanical anchor in the confusion of blind flight. Autopilot systems can hold altitude, heading, and speed more smoothly than any human pilot. Human pilots, no matter how skilled, cannot match the tireless precision of an autopilot system that monitors hundreds of inputs every second and makes corrections without fatigue or distraction. Modern autopilots can fly an entire route from takeoff to landing, adjusting for wind, turbulence, and changing conditions with a smoothness that passengers barely notice. The system maintains altitude within a few meters, heading within a fraction of a degree, holding the aircraft steady while the crew monitors systems and manages the unexpected. In cruise, the autopilot does most of the flying, freeing pilots to focus on the bigger picture of weather, fuel, and navigation. Yet the autopilot remains a tool, not a replacement, and pilots must always be ready to take control when situations exceed the machine's programming. It is precision without rest, tireless attention written in code. Fly-by-wire systems replace mechanical controls with electronic signals, allowing computers to assist pilots. In older aircraft, moving the control column physically pulled cables and pushed rods that deflected the control surfaces, a direct link between pilot and aeroplane. Fly-by-wire replaces these connections with electrical wires that carry signals from the cockpit to computers, which then command hydraulic actuators to move the surfaces. The computers can filter pilot inputs, preventing maneuvers that exceed structural limits or stall the wings, making the aircraft safer and easier to fly. Multiple redundant computers compare their results constantly, ensuring that a failure in one system does not compromise control. Fly-by-wire also allows designers to create aircraft that would be unflyable without computer assistance. It is flight by electricity and software, with the pilot commanding and the computer responding. And from the cockpit instruments, we look forward to the future of flight, where silence and efficiency meet. Electric aircraft are being developed that produce almost no noise and no emissions during flight. Electric motors spinning propellers produce far less noise than combustion engines or jet turbines, and they emit nothing at the point of use: no carbon dioxide, no nitrogen oxides, no particulates. Small electric aircraft already fly regular routes, carrying passengers on short hops with a fraction of the environmental impact of conventional planes. The challenge for engineers is energy storage, since batteries remain far heavier than jet fuel for the same amount of energy, limiting range and payload. As battery technology improves, electric aircraft will become practical for longer flights, potentially transforming regional travel into something quiet and clean. The silence of an electric takeoff is startling to those accustomed to the roar of jet engines, a glimpse of a different future. It is flight without fire, propulsion drawn from electrons. Solar-powered aircraft have circumnavigated the globe using only energy from the sun. In 2016, the Solar Impulse 2 became the first aircraft to fly around the world powered entirely by the sun, its enormous wings covered in photovoltaic cells that captured sunlight and stored energy in batteries for night flight. The journey took over 500 days, with stops and delays, because the aircraft was slow and vulnerable to weather, but it proved that carbon-free circumnavigation was possible with existing technology. The wings span more than 70 meters, wider than a jumbo jet, yet the aircraft weighed less than a car because it had to extract every bit of efficiency from the thin trickle of solar energy available. Future solar aircraft may carry passengers and cargo, though they will likely always require enormous wings and gentle weather. It is flight powered by starlight, borrowed from the sun and returned as motion. Hydrogen fuel cells may one day power large commercial aircraft with only water vapor as exhaust. Hydrogen can be combined with oxygen in a fuel cell to produce electricity with only water vapor as a byproduct, and engineers are working hard to scale this technology for commercial aviation. Unlike batteries, hydrogen stores enormous amounts of energy for its weight, potentially matching or exceeding jet fuel, though storing it requires bulky pressurized or cryogenic tanks. Several prototype aircraft have flown on hydrogen fuel cells, and manufacturers are investing heavily in this technology for regional and eventually long-haul flight. The shift to hydrogen would require rethinking airport infrastructure, from fuel storage to refueling, but the environmental benefits could be truly transformative. Water vapor is the only emission, leaving the sky cleaner for each flight. It is flight powered by the simplest element, burning without fire. Blended wing body designs could make future aircraft more efficient by integrating the wing and fuselage into one smooth shape. Conventional aircraft have a distinct fuselage and separate wings, but the blended wing body merges these into a single smooth lifting shape that generates lift across its entire span. This design reduces drag by eliminating the junction between wing and body where turbulent airflow wastes energy, and it provides more internal volume for passengers or cargo. Wind tunnel tests and flying prototypes have shown fuel savings of 20% or more compared to conventional layouts, numbers that could transform aviation. The challenge is designing cabins that passengers will accept, since the interior would be wider and flatter than the familiar tube, with windows only at the edges. Engineers are studying how to make emergency evacuation safe from such a different shape. It is the aircraft reimagined, lift and body becoming one. Laminar flow control systems may be able to reduce drag by keeping the boundary layer smooth over entire wings. If the boundary layer over a wing could be kept laminar across the entire surface, Instead of transitioning to turbulence, drag would drop dramatically and fuel efficiency would soar. Laminar flow control systems use suction through tiny holes in the wing skin to stabilize the boundary layer, drawing away the disturbances that would otherwise trigger turbulence. The technology is complex and expensive, requiring sophisticated manufacturing and careful maintenance, but the potential savings are enormous for aircraft that spend hours cruising at high altitude. Some experimental aircraft have demonstrated significant drag reductions using active laminar flow control, pointing the way toward a future of quieter, more efficient flight. The goal is a wing that slips through the air with barely a whisper of friction. It is smoothness engineered at the molecular scale. Morphing wings could change shape during flight to optimize performance at different speeds and altitudes. A wing optimized for takeoff is not the same as a wing optimized for cruise, and morphing wing technology aims to combine both by allowing the wing to change shape during flight. Imagine a wing that extends its span after takeoff for efficient climbing, then sweeps back for high-speed cruise, and deploys extra camber for landing, all without the gaps and hinges of conventional control surfaces. Smart materials and flexible structures could make this possible, creating wings that ripple and flex like bird wings rather than staying rigid. Several research programs are developing morphing wing concepts, and small-scale demonstrators have already flown. It is a return to the flexibility of nature, where every wing bends and twists to match the moment. The rigid wing may one day seem as crude as the fixed propeller. And from the aircraft of the future, we return to the atmosphere that makes all flight possible. Without the atmosphere, there would be no lift, no drag, and no sound, only the silent vacuum of space. Everything that makes flight possible depends on air, the invisible ocean of gas that surrounds our planet and provides the medium through which wings push and propellers spin. Without air, there would be no pressure difference to create lift, no resistance to slow a falling object, no sound to carry the roar of engines or the quiet whisper of gliders. Spacecraft beyond the atmosphere must rely entirely on rockets and momentum, with no air to push against, no weather to navigate, no turbulence to feel. The atmosphere is thin, fragile, and finite, a layer of gas no thicker relative to Earth than the skin on an apple, yet within it all of aviation exists. It is easy to forget how remarkable it is that air exists at all, and that we have learned to move through it at will. Everything begins with the atmosphere, and to it we are always in debt. The atmosphere is held to the Earth by gravity, thinning gradually until it fades into the emptiness between worlds. The atmosphere does not end abruptly, but fades gradually with altitude, each layer thinner and colder than the one below, until eventually the density drops so low that molecules rarely collide at all. Gravity pulls air molecules toward the surface, concentrating most of the atmosphere in the lowest few kilometers, where weather happens and almost all life exists. Above the stratosphere, the mesosphere and thermosphere extend to the edge of space, so rarefied that they are almost vacuum yet still capable of slowing satellites over time. This thin shell of gas is all that separates the living Earth from the radiation and cold of space, protecting us while enabling the physics of flight. Air is constantly in motion, heated by the sun and stirred by the rotation of the planet. It is a gaseous ocean, held by gravity and shaped by heat. And as you breathe in the same air that lifts every wing, let your body rest in the knowledge that the atmosphere holds you too. There is nothing you need to do but breathe, and let the quiet physics of the air carry you gently into sleep. This is science for sleep, helping you fall asleep fast. Air molecules travel at hundreds of meters per second, colliding billions of times as they flow around a wing. At room temperature, the nitrogen and oxygen molecules that make up most of the air around us are moving at speeds of around 500 meters per second, crashing into each other billions of times every second in a constant chaotic dance. When air flows around a wing, these collisions transfer momentum and pressure, creating the forces that keep aircraft aloft. The molecules do not know they are part of a flow. They are simply bouncing off each other and off surfaces, yet from their random motion emerges the orderly physics of lift and drag. It is a statistical miracle, billions of tiny collisions adding up to forces strong enough to carry jumbo jets across oceans. The air seems smooth and continuous, but it is made of particles moving faster than any aircraft could ever fly. Flight happens in the gaps between collisions. The viscosity of air is what creates the boundary layer and allows wings to generate lift. Air may seem perfectly smooth and frictionless to our senses, but it has a subtle and remarkable stickiness called viscosity that causes it to cling to surfaces and resist shearing. This viscosity is what creates the boundary layer, the thin region near a wing where air velocity drops from free stream speed to zero at the surface. Without viscosity, air would slip past a wing without any friction, and the circulation that produces lift would never form. It is the stickiness of air that allows wings to grip the flow and redirect it, generating the pressure differences that support flight. Viscosity also creates drag, as air resists being pulled along by the moving surface, so engineers must carefully balance its benefits against its costs. Every wing depends on this subtle stickiness, this molecular friction that makes flight possible. If air had no viscosity, there would be no lift, no drag, and no weather, just molecules passing through each other. Imagine a universe where air molecules pass through each other like ghosts, never colliding, never exchanging momentum, a perfect inviscid fluid with no friction and no resistance whatsoever. In such a world, a wing could not generate lift at all because there would be no circulation, no pressure difference, nothing to push against. There would be no drag either, so objects would glide forever once set in motion, but they could never climb or turn. Weather would not exist because convection requires friction to transfer energy, and sound could not propagate because it needs molecular collisions to carry vibrations. It is a strange and silent universe to imagine, one where the very concept of flight loses all meaning. We fly because air sticks to itself and to us, and without this stickiness, our world would be unrecognizable. The Wright brothers understood aerodynamics better than anyone before them because they built their own wind tunnel and tested over 200 wing shapes. In their bicycle shop in Dayton, Ohio, the Wright brothers built a small wind tunnel from an old starch box and a fan, then systematically tested wing shapes to discover which produced the most lift for the least drag. Previous experimenters had relied on published tables of air pressure data that turned out to be wrong, but the Wrights trusted only what they could measure themselves. Over months of testing, they refined their understanding of camber, aspect ratio, and control, knowledge that would prove decisive when they finally arrived at Kitty Hawk. Their methodical approach, testing hypotheses against reality and discarding what did not work, was true scientific inquiry applied to flight. The wind tunnel gave them answers that no book could. They succeeded because they questioned everything and built machines to find the truth. The first powered flight lasted only 12 seconds and covered a distance shorter than the wingspan of a modern airliner. On the morning of December 17, 1903, Orville Wright lay flat on the lower wing of the flyer as the engine coughed to life and the propellers began to spin. The aircraft lifted off the sand, flew for 12 seconds, and landed 36 meters away, a distance that would fit inside the economy cabin of a modern wide-body jet. That brief hop changed everything, proving that controlled, powered flight was possible and opening the door to a century of progress that would put humans on the moon. Within a generation, aircraft crossed oceans and circled the globe, achievements the Wrights could barely have imagined. Yet every flight since has built upon those 12 seconds at Kitty Hawk, when two brothers from Ohio showed that the sky was not beyond reach. The first flight was measured in feet, but it opened miles. And from the first moments of powered flight, we gaze across a century of progress to the sky we know today. More than 100,000 flights take off every day, carrying millions of passengers through the atmosphere. On any given day, more than 100,000 commercial jet flights take off around the world, forming a vast web of routes that connect cities on every continent. At any moment, hundreds of thousands of people are flying through the atmosphere, watching films, eating meals, working on laptops, or sleeping peacefully as the ground passes far below. The sheer scale of modern aviation is almost impossible to comprehend. A global transport network that moves billions of passengers every year with a safety record unmatched by any other mode of travel. Behind this everyday miracle lies over a century of engineering, regulation, and careful learning from failures. Every flight relies on the same principles of lift and drag that carried the Wrights. The sky has become a highway, and flight has become routine. The safest place on an aircraft during turbulence is over the wings, where the structure is strongest. When turbulence strikes, the aircraft flexes and rocks, and passengers feel the forces more strongly toward the nose and tail, where the fuselage acts like a long lever arm amplifying the motion. Over the wings, where the strongest structural members connect to the fuselage, the movement is minimized and the ride is noticeably smoother. This is why experienced travelers often prefer seats near the wing, especially on routes known for rough air. The wings themselves flex visibly during turbulence, bending upward and downward as they absorb the loads, a flexibility built into the design to prevent structural failure. It can be alarming to watch, but the bending is entirely intentional and safe, far better than rigidity that would transmit every shock. Sit over the wing and let the structure absorb all the bumps for you. Aircraft are struck by lightning regularly, but their aluminum or composite skins conduct the electricity safely around the cabin. Commercial aircraft are struck by lightning on average once or twice per year, yet these strikes almost never cause damage or injury because the aircraft is designed to conduct the electricity harmlessly around the outside. The aluminum skin, or the conductive mesh embedded in composite structures, provides a path for the current to flow from entry to exit without passing through fuel tanks or sensitive systems. Inside the cabin, passengers may see a flash and hear a bang, but the current stays on the surface like water running off an umbrella. After landing, mechanics inspect the aircraft and may find small burn marks at the entry and exit points, but structural damage is rare. It is engineering that anticipated nature's power and built protection into every surface. Lightning finds a path, and the aircraft gives it one that leads safely away. The pressurized cabin of a modern airliner maintains a comfortable altitude of about 2,000 meters while cruising at 11,000. At cruising altitude, the air outside is so thin and cold that an unprotected human would lose consciousness in seconds and freeze in minutes, so the cabin must be pressurized to a level the body can tolerate. Modern airliners maintain an internal pressure equivalent to an altitude of around 2,000 meters, low enough to be comfortable, yet high enough to reduce the stress on the fuselage structure. This means the cabin is always a balloon pushing outward against the near vacuum outside, a pressure difference that requires careful engineering of seals, doors, and structural joints. Passengers may notice their ears popping as the cabin pressure changes during climb and descent, a gentle reminder of the forces at play. It is a carefully managed environment, neither the ground nor true altitude, just enough to keep everyone comfortable and safe. Every breath you take on a long-haul flight has been compressed, cooled, filtered, and mixed before reaching you. The air inside an aircraft cabin is drawn from the compressor stages of the engines, heated by compression to several hundred degrees, then cooled, filtered through hospital-grade filters, and mixed with recirculated cabin air before reaching passengers. This process removes particles, bacteria, and viruses while maintaining humidity and temperature at comfortable levels despite the extreme conditions outside. The cabin air is completely replaced every few minutes, far more often than in a typical building, making aircraft cabins surprisingly clean. The familiar smell of an aircraft cabin is partly the outgassing of materials and partly the mixture of air from different sources flowing through the system. It is breath drawn from the heart of a jet engine, transformed into something pure. Every breath you take at 30,000 feet has been through a remarkable journey. And so our journey through the quiet physics of high-altitude flight gently descends toward its end. From the invisible forces that lift every wing to the frozen corridors of the stratosphere where aircraft glide in silence, to the boundary layers that cling to surfaces like a second skin, we have traced the elegant science of how objects move through air. We have explored the thermal columns that carry gliders upward without engines, the shock waves that form at the speed of sound, the jet streams that flow like invisible rivers around the planet. We have visited the edge of space where pilots wear pressure suits and the sky turns black, and we have returned to the first 12 seconds of powered flight that changed everything. If this gentle exploration of aerodynamics brought you peace, consider subscribing and becoming part of our community of curious minds who find comfort in sleepy science. There are more wonders waiting in the skies and beyond, more quiet facts to carry you into restful nights. Share this journey with someone who needs calm, and we will be here whenever you return. Right now, as you lie here, the same air that lifts aircraft across oceans fills your lungs with each slow breath. The atmosphere surrounds you, holds you, keeps you warm. Every breath you take moves molecules that have been part of clouds, part of storms, part of the wind beneath 1,000 wings. You are made of the same elements that make flight possible. If your eyes feel heavy, let them close now. Let your shoulders release any tension they have been holding. Let your hands rest open and soft. Imagine yourself rising gently through layers of atmosphere, higher and higher, until the noise of the world fades into silence. There is no turbulence here, only the smooth, steady glide of restful sleep. Let your breathing become slow and even, like an aircraft on final approach, descending gently toward the runway. Tonight, as you rest, the sky remains alive with silent journeys. Aircraft cruise through the darkness above, their passengers sleeping as you sleep now, carried by physics through the quiet corridors of the stratosphere. Somewhere, a glider pilot is landing in the last light of a distant sunset. Somewhere, a bird is folding its wings and settling into its roost. The atmosphere continues its eternal circulation, moving heat from equator to poles, lifting moisture into clouds, and carrying the weight of everything that flies. You are a small, warm presence beneath this vast and living sky, peacefully resting among the quiet wonders of the air. Sleep well, sweet dreams. And may you carry with you the gentle knowledge that the same physics which lifts wings through the sky also lifts the air into your lungs, connecting you to every creature that has ever flown and every breath that has ever risen toward the stars. This has been Drowsy Discovery. Good night.